I want to thank the organizers for inviting me, and I'm sorry that I cannot be there in person. Um, I the topic that I'm going to be covering may not be at the center of the theme of the workshop, but I hope that I'll be able to give you some um, description of some topics that you might find interesting. And one of the things that I want to emphasize is the fact that when you're dealing with complex media, you are not necessarily able to quantify the nature of the microstructures. And what I want to tell you about is developments that have been made over the years and some recent developments that enable us to relate various microstructural descriptors to the physical properties of these complex materials. And I'm going to be discussing a bunch of different physical properties. And then I'm going to also talk about how some of these considerations have led to ways of quantifying what you mean by disorder and what you mean by randomness or order. Okay. So I am dealing with heterogeneous materials. And for simplicity, I'll be talking about two-phase media. So you imagine partitioning space into two disjoint regions, phase one region with some volume fraction phi1 and some set of properties k1, and then a phase two with volume fraction phi2 and some set of properties k2. And the idea is that under certain conditions, you can homogenize this heterogeneous system. You replace it with some effective homogeneous system, and the property of interest here is the effective behavior, the effective physical property, K sub E. And of course, there are many, many different examples of such media, porous and composite media, foams, colloids, battery materials, geologic media, biological membranes, animal and plant tissue, and the list goes on and on. So the effective properties that can be that we're interested in is the effective conductivity tensor, the effective diffusion tensor, effective stiffness tensor. If this is a suspension, the effective viscosity, the mean survival time. This is a quantity that you might not be familiar with. Is basically you have a Brownian motion that occurs outside, say, traps, and it diffuses, and you want to be able to predict the average time that it takes for that Brownian particle to survive before it gets trapped at the interface. There are various time-dependent properties, relaxation times, that one is interested in. The fluid permeability, if this is a porous medium, nonlinear mechanical properties, optical and other wave properties. Now, on the right side, I say these are seemingly different physical properties, but in fact, they're actually related to one another. So if you have one measurement of one particular property, let's say that's easier to measure that particular property, it actually is giving you information about a seemingly different property of that system. We call these cross-property relations. And there are ways of rigorously determining these cross-property relations. Now, why is this the case? It's the case because all of the effective properties are sensitive to the details of the microstructure. And by that I mean volume fractions, orientation sizes and shapes of the phase domains, spatial distribution of the domains, connectedness of the phases. And these all are mathematically described by various correlation functions that I'm going to touch on. Okay, so the outline of the rest of the talk is I'm going to say a few words about various statistical descriptors of two-phase media. Then I'll talk about microstructure-dependent estimates on transport properties in particular. Then I'm going to talk about something called hyperuniformity, which you may or may not know anything about. And then quantifying order and disorder across length scales. Now, all of this is meant as kind of as an appetizer, because you'll see, even though I'm not going to really be able to discuss it, that a lot of these ideas can then be used to design heterogeneous materials according to the microstructure. So it definitely has design implications for materials discovery. All right, so let's begin with one of the more common correlation function is the endpoint correlation function. Well, this is just defined to be the average, the ensemble average of a product of indicator functions at different positions. So this is a function that's one inside one phase and zero outside. And this also has a probabilistic interpretation. So for example, if I'm dealing with little n is equal to 2, that's the 2-point probability function. It's the probability that the endpoints of a line segment fall in one of the phases. Okay. The 3-point probability function is the probability that a triangle with side lengths RST, that the vertices of that triangle fall in one phase. In general, it is the probability that I throw a polyhedron and that the vertices land in one phase. These quantities arise in rigorous expressions, including exact expansions and bounds for the effective conductivity, elastic moduli, diffusion properties, fluid permeability, and optical properties. Now, it turns out that there are going to be various problems in which the interface plays a major role. And so you may or may not be familiar with these types of correlation functions. The simplest such correlation function, you can define an indicator function for the interface. So this you can think of as a generalized function that just lives on the interface that I'm calling M. And then you can then define into existence correlation functions that are based upon ensemble averages of this interfacial indicator function. The simplest one would be the 1.1, which is simply the specific surface. Then another one is you have a product of these two m's at different positions, and if it's homogeneous, then it just depends upon the displacement between the 2 points. So I'm going to call that R. This is called the surface-surface correlation function. And these interfacial endpoint correlation functions naturally arise in rigorous bounds on the effective properties in which the interface plays a role, like the diffusion-controlled reaction problem that I alluded to earlier, plus the fluid permeability, because in the case of the fluid permeability, let's say you have no slip at the boundary. Now, I've just mentioned the 2-point probability function. I want to talk about some other 2-point correlation functions. The other one I just mentioned, the surface-surface. Another one is the surface void. Another one is the so-called pore size probability. Given I have a point in the pore space, what is the probability density of finding the nearest interface a given distance delta away? Now these quantities apply for general media. Now, if you happen to have particulate media, then there are certain functions that naturally come up there. So for example, let me just describe one of them in particular. Given that you have a particle at the origin, what is the probability density associated with finding the nearest one a given distance away? This is not the same thing as the standard pair correlation function, because that doesn't care whether or not it's the nearest neighbor. Now, the spectral density comes from the 2-point probability function that I mentioned earlier. The autocovariance function is just this 2-point probability function minus the square of the long-range value of the 2-point function. That's called the autocovariance function. And if you take the Fourier transform of that, that's the spectral density. Basically, you can think of this as the Fourier transform of the image squared, okay? Now, in the large wave number limit, you can show that this decays in a particular power law decay with a coefficient that depends upon the specific surface. And in fact, some people in the past experimentally, because you can get this from scattering information, have computed the specific surface this way. So Debye and people like that did that. Now, another quite interesting quantity is the local volume fraction variance. So you imagine that you have a window of a given radius, and now you're going to move that window from location to location. The volume fraction is going to fluctuate. And now I can define a random variable associated with that particular volume fraction. And what I'm doing is I'm averaging over all positions of the windows. I'm going to look at the variance associated with that random variable. So that's the local volume fraction variance. And you can show that that quantity is intimately related to either the autocovariance function or the spectral density that I just defined. I'm not going to get into this. Is just this quantity alpha 2 is just a geometric quantity that depends upon the window geometry. Now, in terms of transport properties, I'm going to go through this really quickly. I'm imagining now, for just concreteness, I imagine I have a fluid saturated porous medium. And I imagine that I'm going to be doing NMR measurements, and in particular, NMR relaxation in porous media, where I'm thinking about the water molecules diffusing around. I put it in a magnetic field, I turn off the magnetic field, and I let the system relax. The mean survival time I mentioned earlier, this is the average time that it takes for a Brownian particle to survive before it gets trapped. For example, you can have paramagnetic impurities at the interface, which causes it to be demagnetized. In the time-dependent version, I'm also interested in the relaxation times. And the principal relaxation time, the largest one, is I'm calling T1. In the case of conduction measurements, let's imagine now that this porous medium has a pore space that's filled with an electrically conducting fluid with this conductivity sigma 1, and that the solid phase is perfectly insulating. And I'm sure a lot of you have heard of the formation factor. This is the way I define the formation factor, which is basically the inverse of the dimensionless effective conductivity of this system. And it's a measure of the tortuosity or the degree of windiness for electrical transport pathways in the pore space. In the case of Stokes flow and fluid permeability, the steady state fluid permeability is of interest. That's the quantity that's involved in Darcy's law. As well as in the time-dependent version of the problem, you have viscous relaxation times, in contrast to the diffusion relaxation times here, where theta 1 is going to be the largest viscous relaxation time. So you're actually you're solving for the Stokes. This is an eigenvalue problem, but for the Stokes operator. Okay, now I'm going to talk about microstructure dependent estimates on the transport properties, and this is a real whirlwind tour through it. So the first thing that I want to do is I want to talk about what you can do exactly. So imagine that now I'm thinking about a more complicated problem in which I'm sending waves, electromagnetic waves into the system. And I want to compute the effective dynamic dielectric tensor, which depends upon the incident wave number, K sub Q. The point I want to make is you can actually, and by the way, in the steady state, this is also related to the steady state dielectric constant, but also the conductivity, which of course, from which you can get the formation factor. But this is a more general situation. Now, it turns out you can write down exact results for this. It's an exact series expansion. And it's a so-called strong contrast expansion because it's not it's valid actually when the contrast between the phases can be infinite. And usually that's not the way that typical perturbation expansions are derived. And I have no time to describe how to do that mathematically, but the point is that because of this, so let me just say that, okay, so the main point I want to make about this is that this is, first of all, a rational function. So it's very, very different than typical expansions. And on the right-hand side, I have an infinite series. And these terms AN, superscript P, P just denotes whether you have a phase 1 or phase 2. This is a wave vector-dependent second-rank tensor that's a functional involving the set of correlation functions that I just mentioned, and then the product of dyadic Green's functions. So in principle, if you want an exact result, you need an infinite amount of information. It turns out, because of the rapid convergence of this series, even for large contrast, their lower order truncation yields accurate closed-formed approximate formulas. And it turns out you can show that these truncations actually expand about optimal structures, which I can't explain. Those of you who might know about Hashine-Strickman structures, that might ring a bell. But anyway, you can view these as resummed representations of the expansions that still accurately capture multiple scattering to all orders. Now, of course, you generally do not have infinite information. So the question is, can you do something beyond just getting really, really accurate approximations that depend upon these correlation functions? And usually that is done in terms of rigorous bounds. So, for example, in the case of the mean survival time that I mentioned to you earlier, you can write down rigorous bounds that involve integrals over either the autocovariance function or equivalently in terms of the spectral density. Okay, so that's a rigorous upper bound. And then it is bounded from below in terms of the mean pore size, where I defined the pore size probability density function earlier. This is just the first moment squared. The formation factor in the example I showed you earlier is actually obtained from a steady state version of this strong contrast expansion that I just described. And here it's being truncated to fourth order. Okay. So it involves in this parameter up to 3-point information. This is a functional that involves up to 3-point information. And this is one that involves up to 4-point information. And the bottom line is that these are extremely accurate for a certain class of structures. Okay, in the case of the fluid permeability, there's also a similar looking upper bound, as I showed you for the mean survival time. And that's all I want to say about that for the moment. Okay. Now, in the case of the fluid permeability is much more difficult than many of the other properties that I just described. It's probably as difficult as the wave propagation problem. I'd say the wave propagation problem is even more complicated. But the point is that you can show that there's an exact relationship for the fluid permeability in terms of the formation factor. This is a rigorous relation, and a length scale that comes from solving the Stokes eigenvalue problem that I can't describe in this short talk. The point is, when you're dealing with fluid permeability, not all of the pore space contributes to the transport. There are regions in the pore space that is carrying very little flow, and then there are going to be regions that are carrying a lot of flow, right? So if you just base your estimates just upon simple 1-point information, like the volume fraction or just the specific surface, they're not really based upon anything that's rigorous because there's a lot of the pore space and a lot of the interface is not really contributing. So you can write down rigorous bounds in terms of some other properties like the mean survival time. You can write it down in terms of the principal relaxation time for the diffusion problem. The formation factor, of course, is given up above here. And so what we're doing is we're bounding actually this length squared, which is extremely difficult to generally solve for. So, but you can bound them in terms of these other properties. Again, these are cross-property relations. So what you're doing is you're using information from about one property to say something about another property. And it turns out you could also come up with approximations that are based upon the second moment of the pore size and the formation factor. And here, all I want to do is I want to show you that this approximate formula is extremely accurate if you compare it to the fluid permeability of BCC data, for which you have essentially exact results, compared to this approximation formula that just uses the pore size statistic from what you can get that very easily from any image of a material, or if you simulated it, it's very easy to compute it. And so from that formula, if you have the formation factor and the second moment of the pore size, you have a very, very good approximation for the fluid permeability. Okay, I'm going to skip figure 3, and then I'm going to go to what is what we tend to refer to as the maximally random jam sphere packing. Sometimes these are called random closed packed states of spheres. And you can show that, again, this formula actually predicts the fluid permeability of this packing, this random packing, very accurately. Now I want to talk about a concept that probably you may not have heard about. It's not exactly a household word. It's called hyperuniformity. So let me just qualitatively explain what this is. And let me put it in the simplest context. This is the context in which it was first um, introduced. Imagine you have a many particle system, and now you want to consider fluctuations within a window in that infinitely large many particle system. And a hyperuniform system is going to have density fluctuations that are greatly suppressed compared to those of typical disordered systems like liquids. Now, it turns out all perfect crystals and all perfect quasicrystals are hyperuniform. So hyperuniformity provides a unified means of categorizing and characterizing crystals, quasicrystals, and special disordered systems. So you can think of this as generalizing our traditional notions of long-range order, the ones that we had for perfect crystals and perfect quasicrystals, to now include these exotic kinds of disordered systems that behave like crystals. And in fact, disordered hyperuniform many-particle systems can be regarded to be new ideal states of amorphous matter because they behave more like crystals or quasicrystals in the way they suppress large-scale density fluctuations, and yet are also like liquids and gases since they're statistically isotropic with no Bragg peaks. They can exist as both equilibrium and non-equilibrium phases. They come in quantum mechanical and classical varieties, and they typically are endowed with unique bulk physical properties. So the existence of disordered states forces us to really rethink what we mean by disorder and on what length scales. And I'm going to come to that later. So these exotic correlated disordered states arise in a myriad of contexts: classical equilibrium liquids, ground states; classical non-equilibrium systems, quantum systems, sphere packing, random matrices; dynamical systems and quantum chaos; number theory, biological systems; novel materials, and even the large-scale structure of the universe. So the large-scale structure of the universe is in fact disordered and hyperuniform. Now what I want to do is switch gears and talk about the generalization of this idea to two-phase media, and it's pretty straightforward. In the case of a two-phase medium, I'm going to be interested in the local variance that I mentioned to you earlier, the local volume fraction variance. And again, you have a window of radius r, and I'm going to move this from location to location. I'm going to measure the variance in the volume fraction for that window size. And I'm interested in what happens as the window becomes very large. Now, if you have garden variety disorder, this variance goes to zero like 1 over r to the dimension. So 1 over r to the volume of the window. However, in a crystal, you can show that this scales like 1 over r to the dimension plus 1. So it goes much faster to zero than it does for garden variety disorder. Now imagine that you have a disordered system that on large scales behaves just like the crystal. These are weird systems, and they've only come to be investigated, explored, I would say, just in the last couple of decades, and especially in the last decade. Again, for typical disordered system, the volume fraction variance for large R goes to zero like 1 over r to the dimension. An equivalent statement in terms of the spectral density is that the spectral density goes to zero as the wave number goes to zero. It turns out you can actually define the same type of behavior, not for the volume fraction fluctuations, but for the surface, the interface area fluctuations. And again, you have the same kind of behavior. There are general hyperuniform scalings besides the one that I just mentioned. So for example, if you have a spectral density that scales like this power law, where alpha is positive, you can show that there are three classes of hyperuniform two-phase media. So this is the strongest class when alpha is greater than 1. When alpha is equal to 1, you have a logarithmic correction. And then between 0 and 1, you have the weakest form of hyperuniformity. That's called class 3. Now, what this does is that this also focuses attention on the large-scale behavior of things that are not hyperuniform. So now I'm going to tell you the two types of scaling behaviors you can get for things that are non-hyperuniform and disordered. So typical non-hyperuniform means alpha 0. In other words, it turns out that the spectral density is bounded as k goes to 0. On the other hand, you can have something that decays even more slowly than the typical one. We call that anti-hyperuniform. Okay, these include systems like fractals and so on. So therefore, in terms of the large scale structure, you can classify all translationally invariant states of matter according to these large scale fluctuations. Here I'm just showing you some typical behaviors for some models. So if you happen to have, let's say, a simple cubic packing, again, these are hyperuniform systems. The spectral density, of course, is 0 up to the first Bragg peak, shown here. So these are in some sense trivially hyperuniform, but there are ways of rank ordering different crystal structures, which I'm not going to talk about. This is this maximally random jam packing. So again, this is a hyperuniform system. It's going to 0 in a particular way as k goes to 0. This is what we've referred to as a stealthy packing. Here I'm showing some typical non-hyperuniform behavior, so-called Debye medium and other models. But the point of these non-hyperuniform models is that as k goes to 0, the spectral density is not going to 0, it's some positive value. And that changes the large-scale fluctuations dramatically in the way that I described earlier. Okay, now I'm showing you some actual structures that correspond to, for example, something that is anti-hyperuniform. And by the way, you can design systems with whatever type of hyperuniform or non-hyperuniform behavior you would like. This is a typical non-hyperuniform system. This is a hyperuniform system that is not so-called stealthy. This is one that is stealthy and hyperuniform. And here I show a periodic system, which again is always going to be hyperuniform. So you really are spanning a wide class from disordered anti-hyperuniform system to ordered systems. Now I want to say something about the optimality in terms of the physical properties of disordered hyperuniform media. We showed with Paul Steinhardt and Marian Florescu in 2009, something that at that time that was thought not to be possible. So using these hyperuniform systems, you can create dielectric networks, okay, of some, say, high dielectric material, let's say in air. So it's a structured material, it's a cellular material. And you can get the largest isotropic photonic band gaps that you could not get with a periodic crystal. Because in the case of photonic crystals, you have preferred directions and the band gaps are not going to be uniform for all directions. And you can create crazy waveguides as a result of this. Disordered hyperuniform media have an optical phase diagram. This was done by another group. Disordered hyperuniform networks also have maximal effective thermal conductivity or electrical conductivity, as well as maximal effective bulk and shear moduli. It was shown by this French group that disordered hyperuniform materials are nearly optimal wave absorbers, and yet by another group that you can form composite lenses that are disordered and hyperuniform, which dramatically reduce backscattering relative to its periodic counterparts. Okay, so the bottom line is that these are materials that are now being explored for their real interesting novel properties. Now I want to tell you about, and I'm not going to be able to spend a lot of time on this, but quantifying order and disorder across length scales. This is a really challenging question, right? It's not easy to be able to characterize randomness because in principle, you need an infinite amount of information. But let me just introduce the idea of seeking to determine what we're going to call order metrics. Now, because you don't have complete information, you do have to practically consider reduced information, and yet information that hopefully will be sensitive. For example, scalar order metrics. These are order metrics that depend upon, in this particular case, I'm showing a particle system, will depend upon all of the positions of the particles in the system, such that this order metric varies between 0 when it's completely uncorrelated and 1 when it's highly correlated and, in fact, let's say periodic. So you want order metrics that rank order things according to one's at least intuition, where perfect crystals would be at the top, let's say perturbed crystals, defective crystals would be a little below that. Then you have quasicrystals, highly defective crystals, correlated random systems, uncorrelated random systems down at the bottom. Now, importantly, you want to be able to detect the degree of order or disorder across length scales and time scales, right? So you don't want just to talk about the large scale structure, which I have focused on in the case of hyperuniformity. You really want to be able to focus on all length scales in the system and time scales. Okay, so one example of an attempt to do this is when you have a particle system, and here I'm showing a pair correlation function and the corresponding structure factor. Okay, you can see wiggles in these functions. If it was perfectly disordered, this function would be 1 for all r. This would be 1 for all k. So you can define an integral over the square of the difference between, let's say, G2 and 1, or the difference between S of k and 1, okay, and look at the volume integrals in those spaces. And this quantity is going to pick up both positive and negative correlations. And obviously, since I'm going across different R or different K, you're able to capture some information across length scales. So this is one particular sensitive metric. Of course, it only involves pair information. And so if you want to study systems that are much more general than that, again, here I have an anti-hyperuniform system. I'm showing you again the typical non-hyperuniform system, and then all the way down to the most ordered system. You want to be able to understand all of these types of systems. One way of doing that is the local volume fraction fluctuation that I mentioned earlier. Now, in the case of hyperuniformity, the focus was on what the behavior of this quantity was or is for large R. But of course, you don't have to think about just large R. You can actually think about what happens for small r, for intermediate R. And so with this volume fraction fluctuation quantity, you can define things and you can rank. I'm not going to go through all of the different models in these 2D cases, but take my word for it that it is completely consistent with one's intuition, and you can do it at any length scale that you want. Okay, so that's, I think, the most important thing. Then finally, I want to talk about the diffusion spreadability as a dynamic probe of microstructure. So let me just quickly introduce this quantity. This is a relatively new quantity. So what you do is you imagine that you have solute, and it's going to be in this blue phase at t is equal to 0. Then you release it at that time, and you follow how this quantity diffuses into the other space as a function of time. You want to be able to compute the spreadability, which is the fraction of the total amount of solute present that is diffused into phase one at time t. Of course, at infinite time, all of the blue stuff diffuses, and at infinite time, it uniformly fills space. Now, it looks like this is just a mathematical convenience, but it's more than that, and I'll explain to you. The point is that for this very, very special situation, you can solve the problem exactly. And it only depends upon the spectral density, which is unusual because I showed you earlier that in general, you need an infinite amount of information. It's because of the way I defined the problem that it only depends exactly on the spectral density, on 2-point information. Okay. Now, the point is that if I look at this as a function of time, uh, it gives you, so at short and intermediate and long time, it actually is linked to the small, intermediate, and large scale structure of heterogeneous materials. In fact, if you have a power law behavior for the spectral density, you can show that this in turn leads to large time behavior that's also power law in the time. And from the time, the way that it behaves for large time, because it is a power law, the exponent alpha is embodied in that, okay? And that's the exponent that you defines what happens as k goes to 0. This also is not just valid for hyperuniform systems, but also non-hyperuniform systems. So the large T behavior is determined by that exponent. And so you can extract from it, from the long time study of that quantity, you can then get the exponent. And you can determine whether the system is anti-hyperuniform, non-hyperuniform, and hyperuniform. Okay, and so you have you can get a kind of spreadability phase diagram where as alpha goes from minus d to infinity, you can span between anti-hyperuniform and things that are actually much more ordered than standard hyperuniform. Call these stealthy structures. Okay, so I've come to my conclusions. There are a plethora of statistical descriptors of microstructures that arise in rigorous relations, various effective properties that lead to accurate estimates. Cross-property relations link seemingly different effective properties. And I hope that that's something that maybe you have not seen before, but I think is an interesting idea, especially when you can measure one property that might be much easier to measure than some other property that you're interested in. Hyperuniformity concept provides a unified means of categorizing and characterizing crystals, quasicrystals, and special correlated disordered systems according to their large-scale structural behaviors. Disordered hyperuniform materials are ideal states of amorphous matter that are often endowed with novel bulk properties that we're only beginning to discover. Spreadability of diffusion information across timescales is a powerful tool to dynamically probe and classify all translationally invariant two-phase microstructures across length scales. Now, one of the things I did not tell you is that this spreadability is directly linked to NMR measurements. So you can actually show mathematically that these problems are essentially directly related to one another. Order metrics have been devised to quantify the degree of order across length scales. Of course, a lot of work still needs to be done there. These general findings have implications for the design of two-phase media with desirable transport, optical and mechanical properties. I didn't have time to really dwell on that in this talk. I didn't have the time to do that. But I think you can appreciate the fact that once you can relate properties to the microstructure in the form of these correlation functions, then you can do inverse optimization to design systems with desirable properties. We've done that, but I'm not going to have time to talk about it. I want to acknowledge the support of the ARO and NSF. And of course, I want to thank my collaborators. And then I want to thank you for your attention.